Hello and welcome again to ie537 Large-Scale Systems. Today we're going to be talking about decision making under uncertainty, and I want to hit a variety of topics in these last couple of sessions on Module 2, the Modeling and Analysis segment. First is going to be, I want to go over the historical foundations, talk about decision criteria, decision trees, utility theory, decision making with multiple objectives, and then game theory. So first of all, let's talk about what is decision theory, decision analysis. This is an area of study of discrete mathematics, albeit there are occasions when we get into continuum mathematics. And I'll mention that in passing. But we're going to focus on discrete mathematics that models human decision making in science, engineering, and indeed all human social activities. This is concerned with how real or ideal decision makers make or should make decisions, and how optimal decisions can be reached, where optimality is a topic in and of itself, and I'll be talking about that just in passing. Decision analysis, in contrast to decision theory, is a discipline comprising the philosophy, the theory, the methodology, and professional practice necessary to address important decisions in a formal manner. Both decision theory and decision analysis have been with us for some time. There are journals in both these areas, scholarly journals, numerous papers and dissertations are published annually in these topical areas. There are textbooks out on them. So this is a well-studied, well-structured field in and of itself. Let's go back to some of the historical underpinnings of decision theory. And one of the earliest citations comes from St. Ignatius of Loyola back in 1548. And here he's talking about how reasoning, basically, and he says to consider upon reckoning up how many advantages and utilities, interesting word here, utilities, we'll come back to that later, but how many advantages and utilities follow for me from holding the proposed office or the benefice, and to consider likewise on the same contrary, the disadvantages and dangers which there are in having it. He's talking about the office that he held. Doing the same in the second part, that is, looking at the advantages and utilities, there's that word again, there are in not having it, and likewise, on the contrary, the disadvantages and dangers of not having the same. After I have thus discussed and reckoned on all sides about the greater inclination of reason, deliberation should be made on things proposed. Important points here that St. Ignatius making. There's a lot of competing things. There are advantages and disadvantages associated with the decision. This is a very thoughtful way to think about decisions. If you read this passage over and again, you will see the nuances associated with pros and cons and benefits and the criteria and utilities and so on that are embedded in it. So it's a good initial foray, if you will, into this whole notion of how one makes decisions. So that was back in 1548, 450 years ago, roughly. Then we have along come the Marquis de Condorcet, and the Marquis talks about the stages of how one makes decisions. He says in the first stage, one discusses the principles that will serve as the basis for the decision in a general issue. He said one examines the various aspects of the issue and the consequences of different ways to make the decision. And then at this stage, the opinions are personal, and no attempts are made to form a majority. Okay, he's alluding here now to decision making where you have multiple decision makers involved. After this follows a second discussion in which the decision is clarified, opinions approach and combine with each other to a small number of more general opinions, and in this way the decision is reduced to a choice between a manageable set of alternatives. He brings it home a little closer now. Now we're talking about making choices. We're talking about opinions of many people, multiple decision makers. When you start trying to analyze these problems with that level of resolution, you quickly see the problem becomes very difficult. Then he says the third stage consists of the actual choice between the alternatives. So in the end, that's what it's about. Listing the alternatives, somehow being able to analyze and determine the relative value accrued to the decision maker associated with each one of those alternatives. This was put out in the early 1800s, so this is about 200 years old. Then along comes Benjamin Franklin. This is a correspondence that he had. And he's talking about here, this was back in 1772, quite a while ago, in the affair of so much importance to you, wherein you ask my advice. This is advice about the governance of Great Britain, actually. Benjamin Franklin says, I cannot, for want of sufficient premises, advise you on what to determine. So you say, I really can't give you the advice you're seeking in making a decision. But, he goes on to say, if you please, I'll tell you how my way is to divide a half sheet of paper by a line into two columns, writing over the one the pros and over the other the cons. So what Franklin is doing is describing a process, if you will, for decision making. Not giving the guy the answer he was asking for, but describing him a methodology. And this was a letter from Benjamin Franklin to Joseph Priestley. Priestley was a British theologian, a dissenting clergyman, a natural philosopher, an educator, a political theorist. Priestley published over 150 works, but he's most credited with the discovery of oxygen, having isolated it in its gaseous state. But Priestley was far beyond a physicist or a chemist. He was very, very active and proactive in the governance of Great Britain. And he posed to Benjamin Franklin some questions about governance, specific issues. And Franklin decided not to answer the question directly, but indirectly, in giving Priestley a way to think about decision-making. Franklin goes on to say that when I have thus got all of them together in one view, I endeavor to estimate their respective weights. And where I find two, one on each side, that seem equal, he strikes them both out. Now remember, he's talking about pros and cons. So imagine a list of several items in the pros, several in the cons. So he reads down the list, and where he can find equal trade-offs on each side between one pro, one con, he simply strikes them off the list. If I find a reason pro equal to some two reasons con, I strike out three things, the two cons and the one pro. If I judge some two reasons con and equal three reasons pro, I strike out all five. Thus proceeding, I find at length where the balance lies. And if after a day or two of further consideration, nothing new that is of importance occurs on either side, I come to a determination accordingly. So you can imagine the process here. You've got this list of several things, the pros, several things, cons. He goes down the list and he says these two are about the same, so he strikes them both out. These two are equivalent to this one, so he strikes those three things out, and so on. At the end of the day, when he's finished striking all these things, let's say the pros still remain and there are no more cons, well, he's going to go in favor, obviously, or vice versa. So that's his process. I found great advantage from this kind of equation in what might be called moral or prudential algebra. Wishing sincerely that you may determine for the best, I am ever, my dear friend, yours most affectionately. They worked very close, and Franklin did, in fact, have a lot of very, very close associates in Europe, both in Great Britain and France, and they borrowed frequently and heavily from his intellect. Okay, what are the characteristics now of decision theory or analysis? One is, this is a notion we introduced back in Module 1, that of anthropocentric nature, meaning people sort of at the center of it. Since we're talking about decision theory, decision analysis, clearly there are people sort of at the center making the decisions. So this is in contrast to some of the physics we look at from Newton and Einstein and so on. People are not at the center of force equals mass times acceleration. People are at the center of decision analysis. Also in Module 1, we talked about the three different levels of modeling: the descriptive, being able to describe what has happened historically; the predictive, being able to describe what will happen in the future; and the prescriptive, describing what should happen. And those build on each other. You recall, if we can take a descriptive capability and add to it an interpolative or extrapolative capability, that gives rise to predictive capability. Now, if we take a predictive and embed in that a normative structure, some notion of the good, if you will, like we do in optimization, now we suddenly have prescriptiveness. Decision theory, decision analysis is about prescriptiveness. And in that spirit, we also talked in Module 1 about axiology, study of values. Clearly, we have to have a good sense of what is in fact valuable to the decision maker, or the decision makers plural, if we're going to make any sort of reasoned decision about the proper decision to make. So keep those things, those characteristics in mind as we go through this notion of decision theory, decision analysis. Okay, now let's get into some specific decision criteria. The second thing on the list I wanted to get through here in decision theory was give you a sense for what some of these criteria might be. Here are some examples. These are referred to historically as the maxi-min, the maxi-max, the minimax regret, and the expected value. And each of these can be used to provide information that is of value in making decisions under uncertainty. In fact, it's not at all unusual to try to find the decisions that one would make in the context of one or more decision criteria, and then as a decision maker, examine those and make a decision based on the sort of boundaries that those have set for you. So let's take those one at a time in turn and see what they mean. And to do that, let's pick on an example. Let's go back to our Luddites, and let's pick up on Edsel Ludd. Edsel Ludd is an enterprising Luddite who's developed a working relationship with a group of foreign Luddites. Let's call those FLs, not to be confused with Florida. And these foreign Luddites have a new weapon that may be helpful to the Neo-Luddites. This weapon is used to harm people with a lethal bioagent. And Ed pays the foreign Luddite group $200 for each weapon, and then Ed sells those weapons to other Luddites for $250 apiece. So he makes a $50 profit. But there's a complication. The weapon is perishable and can be effective for only 24 hours after it's delivered to Ed by the foreign Luddites. Consequently, at the end of each day, the weapon is worthless. Now, Ed knows that he can sell at least 6, no more than 10 weapons each day. There's a possibility for each of those 6, 7, 8, 9, or 10 are equally likely outcomes. So those are all things that Ed knows, okay? So that's the problem. Now the issue is, so how many of these new weapons should Ed purchase to maximize his profits? So let's introduce some notation to do our analysis with. First of all, let's define this set A as a set of available actions. And it consists, that's capital A. The set consists of elements, lowercase a, with a subscript, 1 through k. So A sub 1 is the first action that Ed is going to be considering. He's going to consider that in contrast to action 2, A sub 2, and so on. And his challenge is to determine that action which gives him the greatest profit. Now, each of those, there's an associated probability, we'll call it P sub j, that's associated with the state that's going to be observed in the end of how many weapons that Ed actually sells. So each S sub j is in this capital S state, and we're going to let j run from 1 to n here. So those are observable end states. And now if action A is chosen, and the state of the world is in fact S sub j, then Ed, the decision maker, receives a reward of R sub ij. So R is the reward. All right, so that's our basic fundamental notation. We have a set of actions, little a. We have a set of end states, little s, subscripted on j, and then we have a set of rewards, R sub ij. So we're going to refer to this as the state of the world decision-making model. And just a side note, this model is applicable beyond just the Edsel-Ludd problem state. So keep this notation in mind. But back to our problem, our example problem. What do we know? First of all, we know that the possible end states, the number of weapons that can in fact sell, are 6, 7, 8, 9, or 10. No more than 10, no fewer than 6. We also know that the probability of each of those end states is 1/5. So Ed's challenge is to choose the action, that is the number of weapons to order each day from these action states, 6 through 10. What are the relationships? Well, we know if Ed purchases I weapons and is able to sell J weapons because they're demanded, then I weapons are purchased at a cost of 200 times I, $200 each. And we know that the minimum of I and J will be the number of weapons sold for $250 each. Why is it the minimum? Well, let's suppose Ed purchases 6 weapons. Or let's make it 7. Suppose he purchases 7 weapons, but only 6 are demanded. Well, he's not going to sell 7, so it's going to be the minimum of 6 and 7. Let's suppose he purchases 7 weapons, but 8 are demanded. Well, he can't sell 8. He's only purchased 7. So it's the minimum again, minimum of 7 and 8. And they're sold at $250 each, so you can see where the profit is going to come out of it. So if Ed purchases I weapons and J weapons are demanded, then he earns a net profit of R sub ij. And R sub ij is simply 250 times I minus 200 times I, which is $50 times I, if I is less than or equal to J. The number that he orders is in fact less than or equal to the number demanded. If I is greater than J, then the return is 250J minus 200I. Now what does that mean? Well, let's build a matrix. We'll call this the action state pair for each possible action and each possible state. So we're going to have weapons ordered. Those are the actions. Those will be along the columns, the rows here. And the weapons demanded, that's how many he can sell, in fact, if he's ordered enough. Those will be along the columns. This is what that looks like. So if he orders 6 weapons, and 6 weapons are demanded, you can go back to the equation to convince yourself that his profit is going to be $300. Intuitively, this is obvious. You can think about it. It's a break even here. He's bought as many as he sold, He's making $50 per weapon. 50 times 6 is $300. And you can go through the rest of the table yourself. There are some interesting points, though. If you look down at the first column with the say 6 weapons are demanded, and he has bought 10 weapons. Well, he's stuck. He can't sell 4 of them, and because they're just not demanded. So he's going to sell the 6, and so he gets stuck with a $500 deficit essentially. That's why the negative 500. Out at the other end of the spectrum here, if he orders 10 and he sells 10, he's making $500. So you can begin to see what's going through Edsel's mind here. If he's very cautious and orders 6 as an example, he's probably going to do okay. He's not going to lose any money. But he's really ambitious. He wants to make a lot of money. The more he can sell, the better off he's going to be. So he can jump that all the way up to $500 that he can make in a day if, in fact, he orders 10 and indeed 10 are sold. So what's he to do? Well, let's keep this this action state pair matrix in mind. I want to introduce one notion, though, about why this matrix is the size it is, and that has to do with domination. Ed does not consider ordering less than 6 or more than 10 weapons. And the reason for that is because those actions are dominated by the ones that he does consider, 6 through 10. So what do we mean by domination? An action, let's call it A sub I, is dominated by another action, A sub I prime, if for all states S sub j in the state space capital S, the reward I sub j is no greater than the reward R sub I prime j. And for some state, S sub j prime, we'll say, R sub I j prime is strictly less than R sub I prime j prime. If you think about that at a moment, it's fairly simple. Simply means that we have this action A sub I being dominated by A sub I prime, meaning that any reward we receive by going to A sub I prime is no greater than the reward received if we just go to, if we make the decision I. So I prime is always dominated by I, if you will, in that sense. And the second part of this, if there's a state out there, J prime, the reward in going from I prime to J prime is always greater than I to J. Okay, so just keep those two notions in mind when you think about dominance. That becomes important later because sometimes these matrices, these action state matrices, can become quite large and intractable. And this is a really effective way to keep that tractability in tow by keeping that cursive dimensionality under some kind of manageable size, if you will. All right. So now let's go to these criteria. You remember the first was the maxi-min criteria. Here we say that for each action, we want to determine the worst outcome. That's the smallest reward. Then the maxi-min criterion chooses the action with the best of these worst outcomes. Sounds a little bit confusing, but hopefully it'll become obvious to you. So the definition here, the maxi-min criterion chooses the action A sub I that has the largest value of the minimum over all world states of the reward, I sub j. Let's see how that translates into our problem here. So the maxi-min solution, if you look at ordering 6 weapons, the worst that can happen, any of those states, 6, 7 are all equivalent, if you will, in terms of reward. The worst that can happen is that Ed will receive $300. Now, what about if Ed orders 7? Well, the worst that can happen there is there are only 6 weapons demanded. If there are only 6 demanded, then Ed gets stuck with one of those. He was not able to sell it. So his reward in this worst state is only $100 now. All the way down at the end now, if Ed orders 10 weapons and only 6 are demanded, his reward there is a negative $500. He goes in the hole. All right, so Ed, thinking about how many to order, constructs this matrix. And he's fairly conservative. We say he don't want to go in the hole $500. So what's he to do? Well, if he applies this maxi-min approach, it's clear that the maximum reward from all those minimum rewards is $300. Clearly 300 is greater than 100 and so on. So what's his optimal ordering policy? 6. He should order 6 weapons if this is in fact his decision criteria, to maximize the minimum possible reward. Not bad if you're kind of a conservative type person. Not going to go in the hole. All right. Let's change now to the maxi-max criterion. What would that do for us? Here, for each action, what we want to do is determine the best outcome. That's the largest reward. The maxi-max criterion chooses the action with the best of the best outcomes, in contrast to the previous, the maxi-min, which was the best of the worst. So the definition of the maxi-max is this is maxi-max. That's a typo there. I'll correct it on the PowerPoint. The maxi-max criterion chooses the action with the largest value of the maximum overall possible world states. So the maxi-max solution. Okay, first of all, what's the maximum of each of those? The maximum reward, if he orders 6, is $300. If he orders 7, he makes another 50. That's $350. All the way up to 10. If he orders 10, what's the maximum? Well, it's $500. So what's he going to do? These are his options. Well, if he picks the maximum of those, that's $500. His optimal ordering policy is to order 10 of those. So now we're getting 2 different answers. If we go with the maxi-min, we get a suggestion that he should order 6, walk away with $300. If we go with the maxi-max, clearly the more entrepreneurial, if you will, the spirit, you might imagine, he's going to walk away with $500 by ordering 10. So what's poor Ed to do? Well, let's go on a little further. There's another criterion that was introduced later than the maxi-min or the maxi-max, and this is called the mini-max regret. Here what we want to do is minimize regret, minimize the maximum regret that you might have as a decision maker. A little more complicated. For each possible state of the world, S sub j, we want to find an action, we'll call it I star of j, that maximizes the reward, R sub ij. What that means is we have an action A of I star j, and that's the best possible action to choose if the state of the world is actually S sub j. Then for any action A sub I and state S sub j, the opportunity loss, here's where the key term, the opportunity loss, how much is this lost opportunity, or the regret for I and S sub j is simply R I star of j, comma j, minus the reward of I, comma j. Let's see what that means. In our example, if we have, if we'll say 7 weapons are demanded, the best decision is to order this I star of 7 or 7 weapons. That yields a profit of R sub 7, which is just the 25 times the 7 minus the 20 times 7, or $350. Now suppose Ed chooses to order 6 weapons. Since R sub 67 is 6 times 25 minus 6 times 20, or $300, the opportunity loss, or the regret, for I 6 and J at 7 is $50. So if Ed orders 6 weapons and 7 are demanded, then in hindsight, Ed realizes that by making the optimal choice, ordering 7 weapons for the actual state of the world, which is 7 weapons demanded, he would have made $50 more than he would have by ordering 6 weapons. So here's our regret matrix. If he orders 6, 6 are demanded, 300 minus 300, that's 0 regret. And if you look down that diagonal of that matrix, you see all those are 0. That means he ordered exactly as many as were demanded, so he has no regret in any of those diagonals. 6 and 6, 7 and 7, and so on. But now what is his regret if he orders 6 and 10 are demanded? Well, his regret there is $200. So you get a sense now for what regret is about. Now, what's actually happening here? Well, if you look at the 500 minus 300, he's got a $200 regret, or the 300 minus 100. I've highlighted in red what these regrets are. So his maximal regret is now $200 for the 6, $200 for the 7, $400 for the 8, $600 if he orders 9, and $800 if he orders 10. Let's back up again and look at this. So the way to do this is I'm getting ahead of myself a little bit. Let me back up again. Bear with me just a second. My finger got a little quick on the button. Okay. So you look across each row. Where's the maximum number? And that's highlighted in red. I did it again. Maybe I can bring it up here. Okay, it's highlighted in the red. For 6, the maximum number is $200. That's if 10 are demanded. For 7, the maximum number is $200 again. That's if 6 are demanded. And so on. So what does that mean? That means the maximal regret, as I showed before, if he orders 6 is $200, all the way up to $800 if he orders 10. So where's the minimum? That's what we're about with the minimum of the maximum regret. Well, the minimum in this case is $200, and that occurs with either 6 or 7 ordered. So his optimal ordering policy is actually either one. And you get the same return regardless in terms of the minimizing the maximal regret. So it's indifferent to 6 or 7. So stay away, though, from 8, 9, or 10. Okay, let's go to the fourth criterion I wanted to expose you to, and that's the maximum expected value criterion. And this criterion leads to the choice of the action that yields the largest expected reward. So what do we mean by expected reward? Let's go back to your probability theory 101. Hopefully you've all been exposed to probability somewhere in your undergraduate curriculum. So this is a definition of expectation of the reward. Should look familiar to you all. Expected value of the actions is simply, in this case, the sum of the probabilities times rewards over all n states. You see, the I does not change because we want the expected value of action I. So we simply take all the n states that you can reach from I and you multiply the probability of reaching it times the reward, sum that over all possible probabilities and rewards in states. So what does it look like for this problem? Well, it's fairly simple. We said that each of those end states are equally likely at 20%, 1/5 probability. So we simply add all of those individual rewards up, or 6, 7, 8, 9, 10, and multiply times 1/5. So in the first case, if we order 6, that translates into an expected value of the reward being $300. If we order 7, expected value of the reward again is $300. If we order 8, the world changes. Now the expected value, because we can lose some money if we're bringing in, if only 7 are demanded, or 6 are demanded, I should say. That's $250, and for 9 it decreases even more. We can lose more money. It's down to $150. And if we order 10, I should say Ed orders 10, the expected value is 0. So right away, you can see what this decision criterion is going to tell you. It's going to say you want to maximize those expected values. So if you look at ordering 6 or 7 weapons, that's going to return $300 either way. If you get beyond that, you're going to lower your return, expected value of the return. So the optimal ordering policy, just as in the previous one, is either 6 or 7. Now it turns out that there's a mathematical reason that expected value outcome is the same as the minimum regret. I'm not going to go through the specifics of that, but you do get a sense that there are different answers depending on the criterion that the decision maker chooses to go with. That's the important message here. And the important message is that many times one of these or more of these 4 criterion are actually used to get an understanding of the boundaries of the decision, where you're likely to lose the most, where you're likely to gain the most. And that's essentially the point I'm trying to make here. It's valuable to explore more than one decision criterion. And in practice, there are many, many other criterion that may be of value. And further, I'll say that often multiple criteria are used. Our criteria here, we said we're going to use one. Well, maybe we want some sort of weighted function of all those criteria. And this notion of multiple criteria and as it's used in decision analysis is very, very well studied. It's worth your while if you're a practicing professional engineer, we'll say, or anybody applying decision theory, to carefully ask the question about are there criteria other than maybe the simple one that comes to your mind first that you ought to be thinking about and applying. And I'll just point to this text. This is a text on multiple criteria decision analysis. And it's fairly voluminous, as you can see. We have over 1,000 pages of analytical discussions and formula associated with how one can, in fact, include multiple criteria in decision analysis. Clearly, we're not going to get into this in this class because I just want to sort of scratch the surface and expose you to what this notion of decision criteria are in decision analysis. I'll say again, if you're using this sort of approach professionally, I encourage you to go to the literature and try to at least think through, in a systems thinking sense, are there other criteria that should be included, and how should we include those? Okay, let's take a short break here. Okay, we're going to continue now in decision theory, decision analysis, by getting into sort of the first enhancement or embellishment of this paradigm, and that is the notion of sequential decisions. And we're going to be using this notion of decision trees. So let me introduce symbolism for us. Okay, we have these squares and these circles that are connected by lines. And so the symbols here, the square we're going to call a decision node, and the circle we're going to call a chance node. There are other names that are used in literature often. The decision node or the action node is a place where the decision maker sits, and he's looking at those A's, those A sub i's, trying to decide which one to pick. The chance node is essentially that probabilistic branching, meaning if he chooses A, what's the likelihood it's going to go, and where's it going to go, and what's the likelihood to each one of those end states. So at the next stage, symbolically, what can happen is, well, let's say we're back here at the very first one on the far left, decision maker deciding, well, if I choose that second one on the list, the second action, then it's a probabilistic branch node, and one place it can go is to another decision, at which time it gives rise to a collection of other possible outcomes, obviously, since you're making decisions, each of which has a probabilistic branch node. And that can go on sort of indefinitely. That's why these things can get very large very quickly, and I'll refer again back to that notion of dominance. It's very valuable to understand how certain actions dominate others, and that way you can prune these trees and keep it fairly small and tractable. At the end of the day, you're eventually going to get into an end node, and those are just denoted here by these little triangles. And associated with those end nodes, there's a consequence. And you can think of those in the sense of what we talked about in the previous session as the rewards. So that's going to be our symbolism. And one thing I want to highlight here, if you look at far right there, you see that one chance node or probabilistic branch node. It has three different arrows coming out, going to C1, C2, and Cn eventually. Well, in fact, each of those other circles on that tree will indeed have multiple lines emanating from them, and those lines correspond to the places that probabilistic branch node can take you. So keep that in mind. This is can be a lot more complicated than it appears in the simplistic symbolism. Okay, now let's keep this in mind, and let me see if I can portray for you an example that'll bring this closer to home. So our example is going to involve, you recall, old Ned Ludd. He was a leader of the Luddites. And this is a rendition, if you will, of an actual engraving that was made back in 1812 of Ned, leading these weavers on their notion of revolt and reform. Okay, so our example problem revolves around this engraving of Ned Ludd. We have an art dealer. We'll call this art dealer Artemis Wild. Well, we can refer to Artemis as just Art. Art specializes in engravings, and Art has a client who's willing to pay $500 for an engraving, this circa 1812 of Ned Ludd. And put a little asterisk by client. We'll make that a little personal here. We'll say this client, you recall we talked about Edsel Ludd in the previous examples. So this client is Ed Ludd. He's the great grandson of Ned Ludd. So this engraving means something to Ed for obvious reasons, and I'm going to bring that back a little later. But for now, we're worried about Art. And what Art can do is he can buy this engraving today for $400, or Art can wait a day and buy the engraving tomorrow, assuming it's not been sold or purchased by someone else. And tomorrow, Art can buy it for $300. And you begin to see the decision problem setting up for Artemis here. If Art buys it today and sell it to Ed for $500, he makes $100 on the deal because he only pays $400. But Art realizes that if he can wait a day and pay $300 for it, he's still going to sell it for $500 to Ed, so he makes $200. So you can begin to see how the decision problem is setting up. And Art may even wait another day and buy the engraving, assuming it's still available, for $260. It's coming down even more. But at the end of the third day, the engraving no longer be available to purchase. Now, each day, there's a 60% chance, a 0.6 probability, the engraving is going to be sold. So here we're introducing the uncertainty and reducing some risk, if you will, to Art in losing any kind of profit on it. So the question is, what strategy or what collection of actions or decisions will maximize Art's profit? Okay, let's look at this decision tree. So his decision on day one, should he buy it or not? Well, if he doesn't buy it, if he does buy it, he can make $100. He buys it for $400. He sells it to Ed for $500, so he makes $100. But what if he doesn't buy it? Well, if he waits until the second day, he can sell it. He can buy it for $300 and sell it to Ed for $500. He makes $200. But there's some chance it's not going to be available. It might be sold to somebody else. So he's got another decision to make. There's a 0.4 probability it'll be available. 0.6 it won't. If it's not available, we've got an end state there. The end state is Art makes no money, no profit. But if it is available, in the day two decision, he can buy it, make $200, or not buy it. If he doesn't buy it, again, there's a question. So what's going to be his return if he does not buy it in day two? Well, again, it depends. If it's not available, which is a probability of 0.6 on the second day, but remember that's got to be convolved with the probability 0.4 was still available on the first. If it's not available, Art walks away with $0. If it is available, there are two possibilities. He can buy it or not buy it. If he chooses to buy it, he's going to receive a $240 return. If he doesn't buy it, obviously he's not going to make anything. So now how do we put all this together to get back to a decision for Art that he's got to make today? You've got these projections in day one, day two, and day three out there. Well, let's begin to fill this tree out. On day three, the optimal decision there will be to buy it. He'd rather have 240 than 0. If he elects to do that, you have to remember there's only a 0.4 probability it's going to be available. So you multiply the 0.4 times the 240, and that's where the 96 comes from, $96. Versus if it's unavailable, making 0. Well, you take the maximum of those two, and it's $96, clearly. So back it up to day two, what's he going to do? Well, if he decides to buy it, he'll get a $200 return. If he decides to not buy it, he only gets 96 expected. So he would elect to buy it on day two, not wait. See the notion of expected return coming in here. Now let's back it up to day one. On day one, he has, again, there's this probabilistic branch. If there's a 0.4 chance that it's going to be available, and if it is available, he's going to buy it at $200. So 0.4 times 200, that's the $80. So if you compare and contrast 80 with its unavailability of 0, clearly 80 that's going to be the expected value. But now he comes back to his ultimate first day decision. What does he do? Well, he has to weigh whether or not to buy or not buy. If he buys, he has a $100 profit. If he doesn't buy, his expected profit is only $80. Since the 100 is greater than 80, his optimal decision, again using expected value in this sequential decision tree, his optimal decision is to buy that engraving right away and sell it to Ed. Pay $400 for it, sell it to Ed for $500, walk away with $100. If he tries to wait, expected value goes down. Now, the neat thing about these trees is the notion of sensitivity analysis. You've all been exposed to that, hopefully. And with sensitivity analysis, what we can do, I won't go through that here. I'm reasonably confident you've all been exposed to that. You can go in and essentially make any of these dollar returns in variables. You can make the probabilities variables, and you can change them. If you're not sure what the probability of availability is or what that price is going to be, change it and look at the effect all the way back here on day one to see when is it that that don't buy is a better decision. But we're going to keep it simple at this point. No sensitivity analysis. And the optimal decision in an expected value sense is to essentially buy that engraving today. That's what's shown in the green. Now here's some complications. First one, what if Ed dealt directly with the current owner of the engraving rather than dealing with Art? So we're going to cut out this middleman, Art of Wild here. Sounds like it might make things easier, but not really. Now the reward function is not as simple. With Art in the middle, we simply maximized Art's profit, the expected value of Art's profits. But Art's no longer there. Now there are at least two attributes that are of importance. One is the cost to Ed of purchasing the engraving directly. And the second one is the aesthetic value of the engraving to Ed, remembering that Ed is the great-great-great-grandson of Ned. So let's introduce some more notation here. Let's let C, little c, be Ed's dollar cost to purchase the engraving. And let's let little e be the aesthetic value to Ed of owning the engraving of his great-great-great-great-grandfather. So we've got two things at play here. Two things of utility, two things of value to Ed. One is Ed's dollars. He didn't want to go out and pay a fortune for this. He didn't have to. But the second is, well, he'd sure like to have it because it has a lot of aesthetic value to him to have an engraving of his grandfather. So now we have a new objective function. Let's call it Z. And that's some function of that cost and that aesthetic value. Now, why is that a complication? Let's go back to the fundamental law of systems that are introduced in the last part of Module 1, that you cannot optimize a system by optimizing its parts. And I pointed out that was a corollary to Aristotle's first law of systems, that a system is more than the sum of its parts. Now, to optimize the system, let's suppose we can break it up into its subsystems. So you can imagine in this case we have one functional form that is the cost function for Ed, and the other functional form, F2, is the aesthetic function. And so this first one, F1, will say cost is the overall criterion restricted to cost, and F2 would be that restricted to aesthetics. So X sub I is a subset of control variables that are available to the ith, and the X sub I should Ed buy that etching today, tomorrow, or the next day. And N is a number of subsystems. Well, in this real simple example, N is simply 2. It's cost and aesthetics. Let me highlight, though, this is unusual. It's typical for the N to be a lot larger than 2. And then we have this representation of how do we combine some cost function with some aesthetic function. Do we add them together? Do we multiply, or some other operation? And as I pointed out in Module 1, that convolution operator can take many forms. It can be an additive form, a multiplicative form, or some other strange form. And I've seen all these. So back to our notation. C is the cost, E is the aesthetics. We have this new objective function. How does that translate into alternative forms for this problem? Just give you a sense for what it means. The additive form, well, we would need some sort of coefficient for aesthetics, some sort of, and that's K sub E here, some sort of coefficient for cost. That coefficient does a couple of things, each of those do. One thing it does is make the aesthetics and the cost equivalent dimensionally. So if cost is in dollars, aesthetics can be in dollars. You've got to have some kind of aesthetic, we'll say cost per aesthetic utility unit, if you will, in E, and then K sub E would essentially do the translation for us. So if K sub E is dollars per aesthetic unit and E is aesthetic units, when you multiply those two together dimensionally, you're left with dollars. So it's legitimate then to subtract the dollars over in cost. The K sub C there would be, we'll say, dimensionless. And so you're subtracting dollars from dollars. That's the first thing. You got to ensure that the dimensionality is honored if you're adding these different terms. Second thing that the K captures is the relative importance. So it is conceivable that K, the aesthetic value, K sub E, is 10 times more valuable than the cost to Ed Edsel, in which case somehow that order of magnitude has to be captured in the K sub E. Okay? So two important things, dimensionality and relative importance. Okay, that's with the additive form. Another form is multiplicative. Suppose we want to say, we don't want to simply add those two terms together. We want to somehow multiply them. Well, in this case, just because the cost, we want to minimize that. We want to maximize aesthetics. Just as in the additive form, we had a negative. We're going to put the cost in the denominator here. All right, now we introduce yet another parameter, and that's the alpha. So the L sub E, lambda sub E, I should say, is the weighting function associated, first of all, with aesthetics that takes dimensionality into account. Lambda sub C is the same thing for cost in the denominator. Now the alpha is typically used to get the relative importance factored in. So alpha sub E in the numerator is the relative importance of the aesthetics, while alpha sub C in the denominator is the relative importance of cost. Now, intuitively, people, if you reflect back on your Boolean algebra for a moment, when you think of a conjunctive form in a statement, you want the aesthetics to be high, and you want, and we'll go to the additive for a moment, you want the aesthetics to be high, or the cost to be low. You think about what you do with an OR operator, you essentially add them together. So that would give rise to an additive form. So if you want this, or that, or this, and so on and so forth, that kind of intuitively gives you an additive form. Multiplicative is more into the and world. You want both aesthetics and cost, if you will. You want aesthetics to be high, and you want cost to be low. That can lead you to a multiplicative. Now, there's a fallacy there. So don't think simply about you want this, or this, or this, and that leads you to an additive. Or you want this, and this, and this, and that leads you to a multiplicative. It's more delicate than that. Nevertheless, one can get multiplicative and one can get additive forms, and the best way to explore which of those, if those are the only two you're considering, is more attractive, is you can go to sensitivity analysis and plot out some curves and see if they make sense intuitively. Okay, so those are two of them. What's the third? Something else? Well, I've made up this weird thing with a trigonometric and a log and an integral over some Stilchi space, we'll say here. So we've got some strange form that could conceivably be an objective function for us, and how we combine the individuals, the individual terms. What's typically done, in what I've seen out there, is that additive form is typically done by people because it's fairly easily explained and fairly intuitive. Multiplicative, that's sometimes done, but not nearly as often as that additive form. Now, there's something else is next to never. I've seen rare occasions where people will cook something up beyond an additive or multiplicative, but boy, it sure takes a lot of almost Herculean effort to make a compelling argument for some other complicated form. Nevertheless, it's been done, but not very often. Now, as conditions change, the number of objectives change, the number of criteria per objective. We add in uncertainty. We add more decision makers. The dynamics of the situation changes. Or we have strategic interactions between decision makers. Clearly, all these things can add to the complexity of the decision analysis, and they do. And it's not at all unusual to have all 6 of these things at play in a real-world problem. So this notion of systems thinking, I can't overstress in terms of decision analysis and decision theory. And I'll go back to the previous lecture we had with Dr. Weiss when he talked about risk analysis. There's a lot of similarities, if you probably notice, between risk analysis and decision analysis. But when you start introducing these other notions, which are very real things and really do occur out there, a lot of the assumptions that we make in these simplistic models just don't play any longer. So I'm really urging you to think in the systems thinking modality when you're solving these problems. You saw those things pretty much, many of them emerge in Goldsmith and Speyer's lectures on intelligent agents. Clearly the stuff that Dr. Cranwell talked about with the system of systems analysis tool set, a lot of that stuff's at play there where you can have multiple objectives. And, although Bob didn't highlight it, the number of criteria, the uncertainty, the decision makers, and dynamics clearly highlighted. And there are in fact strategic interactions among decision makers in those large problems. So all these things can play to really complicate our lives in applying any of the tools I've shown you so far. I'm going to show you another one yet in just a moment, but I can't encourage you enough to be a systems thinker when you're applying any of these tools. And they all become what I call bumps, big, unmanageable, messy problems. I'm going to show you an analytic framework that sort of highlights this notion of multiple decision makers, multiple criteria. In the middle of this is that social movement theory kernel, and this is just an abstraction of it, where we have essentially a systemic characterization of social movement theory and the interactions among the various dimensions. So what do we have in a decision-making set with this social movement theory kernel playing as the socioeconomic engine in the middle of all of it? Well, there are, we'll call it non-anthropogenically induced stresses. This means stresses induced on this social movement theory model that have nothing to do with people directly. There could be a tornado, as shown in this little cartoon. It could be an earthquake or a hurricane. It could be disease of some sort, epidemic that's spread. People are clearly engaged there, but it's anthropogenically in the sense that people cause the epidemiology, but it's not malevolent. It just sort of naturally occurring. And so that's what's meant by these non-anthropogenically induced stresses. But we can also have anthropogenically induced stresses, and I've shown here the cartoon of the group of neo-Luddites who are stressing our system that we've talked about. And they're stressing this model, this representation we have of our system, the social movement theory kernel. So you can get stresses that are either non-anthropogenically induced or are indeed anthropogenically induced, things that cause changes in our system state. So what are we trying to do here? Well, we're trying to somehow manage those stresses. And what I've shown here, again, is a cartoon. There's a gentleman carefully exploring these 6 different venues, if you will, for managing these neo-Luddite stresses to our system. And these range from regulations to fiscal incentives to information, education, and outreach to technology development and deployment to inter and intra-organizational relations, and then finally enforcement. So if you will, you think about that action space that I've shown you in the decision theory, decision analysis world with a capital A, with a subset of all these A sub 1, A sub 2, all the way up to A sub K different actions. That's essentially what's shown on the left side of this graphic with this gentleman. Now imagine those A's being categorized or grouped into these 6 different categories. So one category is a set of regulations that he might impose, a second set of fiscal incentives, a third set of information, education, and outreach actions, a fourth is technology development and deployment, a fifth is intra-organizational relations, and the 6th is enforcement. So now I've got essentially 6 different clusters of actions. Each cluster might have a host of sub-actions. There might be several regulations, several sets of fiscal incentives, taxes, subsidies, and so on that the decision maker can pick and choose from. Moreover, the decision maker can pick not just one, but a combination of those. So let's say hypothetically in each one of those 6 different categories, say hypothetically I have 4 actions. So 6 times 4 is pretty close to 24 different actions. What you have to be careful of is not saying, well, that just means I've got to pick one of those 24 and optimize things. Not that simple, because there are combinations of those that may be superior to any of them. So now imagine, if you will, the combinatorics of 24 different items, taking 2, 3, 4, n at a time. It can become pretty messy pretty quickly. Okay, that's not all the picture though. Let's add a little more complication on the right-hand side over here, and this has to do with the return, if you will, the objective function. So think of these as the R sub ij. And what I've shown here is a list of 7. I think I showed you these before, but I'm trying to bring it home a little bit more in this module. So what we have here is a list of 7 different categories that contribute to, so we'll say, quality of life, that this decision maker is impelled, encouraged, in fact, he has to recognize somehow. He has to worry about human rights, about human health, about the economic well-being, about preserving their culture, about environmental quality, about the confidence in government, and about the availability of services. Now, for each of those, just as in the action side, for each of those 7 reward categories, you can imagine multiple measures of reward. And again, let me pick an arbitrary number. Suppose there are 5 measures for each one of these award categories. 5 times 7 is 35. By the way, you're never going to, it's very unlikely you'd have the same number, but for each one of the categories. But let's just keep it simple. So we have 35 different types of reward. Now what we're going to want to do is somehow combine those rewards, just as we did in the portfolio sense. And we come back then again to the question, do we simply add them together and come up with some multiplicative constant? Do we multiply some of them and have an exponent for weights? Or is there some other kind of strange form we want to come up with? And by the way, in terms of strange forms, those decision criteria I showed you before, the maxi-min, the maxi-max, and the max minimum regret, and the maximum expected value, are all sort of nuances that are not as trivial as simply adding things together or multiplying them. So it is easy to come up with other forms. It is not so easy to come up with how one combines these myriad different measures. I'm bringing these home to you to show that I've given you some tools, but in order to properly use these tools in the real world, you got to really be a systems thinker and think more broadly than one measure like cost, like we did with art, or even two measures with art taken out of the picture where Ed simply chose cost and aesthetics. Sure is nice if you have those situations, and when you can get away with them, go for it. And we could with Ed, because there were basically only two things. We could with art. He was only interested in profit maximization. But in your world, please be sure to always answer the larger question. Draw your boundary sufficiently large that you don't paint yourself into a corner of having focused exclusively on that one thing that's important, but you sure miss some other things that are extremely important. And I'll take you again back to the little cartoon I showed you about the drunk who staggered out of the bar at 2 a.m., dropped his quarter, ended up going down and looking under a lamplight because that's where the light was. Well, he missed the big picture. So don't fall into that trap. Okay.